So welcome to lesson number 7 from Light and Sound, where we're looking at the properties of light. We're now on the very last part of this. We're going to look at 7 part 3, which is the electromagnetic spectrum. So let's go to your notes on the electromagnetic spectrum. What a short section. So the electromagnetic spectrum is all about light. Light travels, obviously, at the speed of light, which is 3 by 10 to the power of 8 meters per second. So we call that value C. C is 3 by 10 to the power of 8 meters per second. How do we make light? Well, we talked about this before in previous lessons. We need some kind of oscillating object to make a wave. And if we're talking about making a light wave, we're going to take an oscillating charge, like an electron. So there's a little electron, which I represent by E. Now that starts vibrating up and down. It'll disturb the electric field around it. And we'll talk about electric fields later on when we do electricity. But for now, it disturbs the electric field around it, and a disturbance or a wave travels out. That's your light wave. It travels at the speed of light. Now, it could be a light wave that you see, that's visible to us, or it could be a light wave that you can't see, invisible, like X-rays you can't see, radio waves you can't see. It's only the colours of the spectrum that you can see. That wave there, of course, will have its usual properties. It'll have a wavelength, which is the distance from crest to crest, and we call that lambda. And it'll also have a frequency f. And you know what the frequency f is? It's measured in hertz. And the frequency is the number of waves per second. Well, the frequency of the wave depends on the frequency of the oscillator. So if that bops up and down 1,000 times per second, you will produce 1,000 waves per second. And the formula that brings everything together is your wave equation. It's in your table book. C is equal to F lambda. We've used that quite a lot already. Okay, so what do I need to know about the electromagnetic spectrum? Well, there's not a great deal you need to know. If I look at my notes again, I have parts of the electromagnetic spectrum. You can see the wavelength of the waves changing as you go from left to right. So on the left, that electron or charge must be bopping up and down lots of times per second. And as you move to the right, less times per second. And depending on which part of the spectrum you're talking about, we give it a particular name. Even though we're giving it a particular name, they're all light waves. Some you can see, some you can't. They all travel at the speed of light. But how do they differ? They differ in terms of their wavelength and their frequency. So let's look at the electromagnetic spectrum in detail. So here I have my vibration charges, lots of vibration charges. And let me pick a particular one. Let me pick this one right here. And it's bopping up and down so many times per second. And let's say as a result of that, it produces a wave that actually is red light. When that goes into your eyes, your brain registers red. So that there is a red wave. If I go down to the next one and it's vibrating up and down a little bit more quickly, then I get a violet wave. I don't have violet, so I'm going to draw blue. So I get a violet wave. So it's, first of all, if it's vibrating up and down, you can see the wavelength gets smaller and the frequency gets higher. So let's call that violet. Now, they are the two end colours on the electromagnetic spectrum. So in other words, this here represents visible light. Light that humans can see, their brains can register. If you talk about in between, well, in between you have all the other colours of the rainbow, your yellows, orange, green, and whatever. So I'm just showing you the two outer colours, and those two outer colours you should know. Now, what would happen if I went beyond red here, and the electron was vibrating up and down a little bit more slowly? You'll get a wave that looks like this. See, the wavelength is a bit longer. If that goes into your eyes, you can't see anything. Your eyes don't register it. We're not sensitive to light of that wavelength. We call that infrared. It's just beyond the red there. In short, we often call it IR, infrared radiation. We can't see that, but they're waves that come from hot bodies. So if a body gives off heat, it gives off those waves that you can't see. You have to know, how do you detect those waves? Well, the way you detect them is there will be a temperature rise in a thermometer. So if I put a thermometer close by, the thermometer would register a temperature rise, indicating they're heat waves. If I go just below the violet, and let's say now my electron vibrates up and down more quickly, then I will get a wave with a smaller wavelength, higher frequency. The frequency depends on the oscillator, of course, the vibrating charge. We call that, it's beyond violet, we call that ultraviolet radiation. And commonly, we call that UV radiation. That's the kind of radiation that will give you a suntan, can cause skin cancer. The ozone layer in the outer atmosphere helps to block the ultraviolet radiation coming in and keeping us safe. And then when there was a big hole in the ozone layer, that was dangerous for humans. Too much UV radiation was getting through. You have to know, how do you detect that? Well, actually, it causes fluorescence, a brightening. In something like, well, white shirts, wash detergent, or Vaseline. So that's how I will detect that kind of radiation, fluorescence in Vaseline. You know, as you go down through that range, they're getting more dangerous, aren't they? So ultraviolet causes skin cancer, sun tanning. Infrared are just heat waves. They're harmless. The colours of the rainbow are harmless as well. So as you move down, as the waves become more energetic with a higher frequency, they become more dangerous. We'll be talking about that later anyway when we do modern physics. Let's go back up here. Let's say my electron vibrates even more slowly. So we get a wave now that looks something like this. We call that microwave radiation. That's used a lot in telecommunications. And then if it vibrates even more slowly again, you're going to get these very long wavelengths that we talked about before. The wavelengths could be as long as 10 kilometers long. They can leap over mountains. They're so weak, you need to pick them up with aerials and amplify them before you can make sense of the signal. These things here would be called radio waves. You can see these things here, you can be swamped in them forever and ever and ever, and they would never do you any harm. They've so little energy. And then if I come down the other end of the list, and beyond the ultraviolet, my electron vibrates even more quickly, then I will get a wave that's got an even smaller wavelength. When they were discovered, they had no idea what they were. You know, when that radiation went near someone's hand, they could see the bones in their hand. They didn't know what they were, so they call them X, like X in algebra. So we call them X-rays. But later on, X-rays, they discovered they were just another form of light that was invisible, but it travels at the speed of light, which is 3 by 10 to the power of 8 meters per second. And then if you vibrate even more quickly again, you're talking about a radiation with a tiny, tiny wavelength. These are extremely dangerous. They're called gamma rays. Gamma is represented by the Greek letter, that letter there. So gamma rays, now they are very dangerous. If they came in here and swamped me, everything will be vaporized. You get them in the aftermath of a nuclear bomb, where everything near the epicenter would be literally obliterate it. So they have an enormous energy. They're extraordinarily dangerous. So what exactly do I need to know about the electromagnetic spectrum? Well, you don't really have to learn the list as such, but I would know the visible spectrum has red and violet as the outside colours. And then invisible, yes, I'd know infrared and I'd know ultraviolet, which are easy to remember because of where the red and the violet are. Know how to detect them. And then, in general, just know about the others. You won't have to learn the ordering like that. If they ask you a question on it, they usually will give you some kind of diagram in the exam question. So, very briefly, you need to know something about the electromagnetic wave itself. A lot of this you probably won't know or understand deeply, but we do electricity and magnetism later on, and electromagnetic induction and that kind of stuff. But what I need to know is be able to draw this diagram here of an electromagnetic wave and what it's made up of. So, let me explain it to you. So here I have an oscillating charge like an electron. The charge is surrounded by the electric field, an electric field. And when the charge goes up and down, it disturbs the electric field, just like dropping a stone into a pond where the ripples travel out. So as that charge goes up and down, you will get this electric field that travels out like that. So that wave represents your electric field. But there is another component to it. When you do electromagnetism later on, you'll find out that a changing electric field gives rise to a magnetic field, and this magnetic field will be at right angles to the electric field. So if I was to draw a wave at right angles to it, I'll draw something like this. That's not a bad effort. I'll shade that blue wave in. So this blue wave is at right angles to the red wave. And that blue wave there is going to represent my magnetic field. That's why we have it. That's why we call it an electromagnetic wave. And that's essentially, at this stage, all you need to know about an electromagnetic wave. So be able to draw that and know there's an electric field at right angles to a magnetic field, and the whole disturbance travels out at the speed of light, which is 3 by 10 to the power of 8 meters per second. So that's just about it, bar, I suppose, your STS, your real-life applications. There's quite a few here, but again, just read it. You want to know something about infrared radiation. You know, they're emitted from hot bodies. They're used in infrared cameras, thermal imaging. The greenhouse effect is important, so read about that. And then you have your ultraviolet radiation. We mentioned the ozone layer also. So there's no need to learn any of this in detail. Just read through it a number of times so you're familiar with some of the applications of electromagnetic waves. Okay, so that ends the lesson.